Okay, welcome everyone. Today it's a pleasure to have Laci Lovas with us. He's a grad student at MIT and he's a visiting student at Stanford where he is advised by Jacob Fox. And he'll be an intern at Microsoft Research New England this summer, like he was last summer as well. He does work in extremal combinatorics, and today he'll tell us about Green's arithmetic triangle removal lemma, which builds on lots of exciting recent work on the Capset problem. Laci.
Thank you for inviting me to give a talk. So, as you mentioned, I'm going to talk about some recent breakthroughs by Croot-Lev-Pach, Ellenberg-Gijswijt, and others, and how that can be used to give a polynomial bound on an arithmetic triangle removal lemma of Ben Green. And this is joint work with my advisor, Jacob Fox. So, doesn't work. So an introduction. So many of you might be familiar with Roth's theorem, which says that if we have a subset of the integers from 1 to n, and we have no three-term arithmetic progression, then the size of the density of A goes to, the maximal possible density of A goes to 0 as n goes to infinity. And Roth's original proof gave the bound of big O n divided by log n using Fourier analytic methods. And the best known bound is best known bounds were developed later by Sanders and Bloom that give a bound of n over log n times some log n factors. Upper bound. And in terms of a lower bound, a construction of Barron gives n divided by this e to the root log n. So these two are very far apart. Now, later, Semeredi's famous theorem extended this to k-term arithmetic progressions using a regularity method. So he developed the precursors of the regularity lemma, which was very important work with many important applications. So one important application was the triangle removal lemma for graphs. What is the triangle removal lemma? So roughly it says that if we have a small number of triangles in a graph, then we can remove a small number of edges to delete all triangles. So to be precise, for any epsilon, there exists a delta, such that if a graph on n vertices has at most delta n cubed triangles, then it has at most epsilon. That should say then we can delete epsilon n squared edges to remove all triangles. And this was proved by Ruja and Semeredi using the regularity lemma, the regularity method. And this is a very important use of the regularity method. It has many important applications in extremal graph theory, in additive number theory, theoretical computer science, and discrete geometry. And this similarly has a very large gap in the upper and lower bound, as we will see. So, so these two. This is also very closely related to Roth's theorem. Now, so here we have these terrible gap between upper and lower bounds. Sorry? Yeah, so it's basically a tower type upper bound and something like, so delta 1 over epsilon to the log 1 over epsilon lower bound. But so instead of this is kind of looking at it in n, we can look at it in fp to the n, so in kind of vector spaces over finite fields. So this brings us to the Capset problem. So many of you are probably familiar with the game of set, where we have 81 cards. So each card has 1, 2, or 3 elements on it. They can have 3 different kinds of shapes, 3 different kinds of colors, and 3 different kinds of fillings. And you put 12 cards on the table, and someone has to find 3 cards so that for each of the 4 properties, they're either completely different or all the same in that property. So for example, here, they're completely different in each of the 4 properties. You can also have some properties that are completely different, some properties they're the same. And the question is, how many cards can you have on the table without having a set? And more generally, how large, so if instead of, let's say instead of 3 properties, we have, 4 properties, we have n properties, how large can a set X in F3 to the n be without a cap set, which is kind of the generalization of this set property. And this is equivalent to being a 3-term arithmetic progression in the case of F3. It's actually equivalent in F3 to many different things, which for different fields is not equivalent. But should mention F3, here we just mean let's say the integers modulo 3. And in general, Fp, where p is a prime, will refer to the integers modulo p, which forms a field. And Meshulam proved a bound of big O 3 to the n divided by n. And this was later in a very long paper extended by Bateman and Katz to 3 to the n over n to the 1 plus epsilon for an explicit small epsilon. This problem is kind of closely related to many famous problems in combinatorics and computer science, including it's related to the matrix multiplication problem. So for matrices, so the question, if you're given 2 matrices, how much time do you need to multiply them? There's an obvious algorithm on the order of n cubed. It's suspected that it would be n to the 2 plus some small 2 plus little o1, but that's not known. An explicit number between 2 and 3 is known, and so kind of lower bounds here could imply, so this problem implies there gives a method for kind of improving the matrix multiplication bounds. It also has implications for the sunflower conjecture, and it's also related to estimates for Roth's theorem. I mean, it's kind of a special case of Roth's theorem in the case of F3 to the n. Now, in terms of a lower bound here, you can easily find a lower bound of 2 to the n by just fixing 2 of the 3 possibilities for each property and taking only those. You can get something better by taking a small example over n equals 4 or 5 and then taking kind of a product construction, and that gives a larger constant, a constant greater than 2 to the n. But until recently, in terms of an upper bound, nothing better was known. And so there's a recent breakthrough result by Croot-Lev-Pach. So they worked in Z4 to the n, and they showed that there you can actually get an upper bound that's kind of exponentially smaller. And with an explicit C, that's about 0.96. And this paper is a bit more than a month old. Now, their method was then later extended by Ellenberg and independently Gijswijt to prove that in Fp to the n, if you're 3AP free, then you get an upper bound. Then you basically have, so you have p to the n total elements, and you can get sort of a much smaller upper bound, again, exponentially smaller for explicit CP. So in particular, this gives a better bound on the Capset problem. And later, Blasiak-Church-Cohn-Grochow-Umans and independently Alon and independently Naslund showed that this proof extends to the multicolored sum-free problem. So what is that, the multicolored sum-free problem? So if we assume that we have now 3 different sets, X, Y, and Z, And we have the property, so they're indexed, and 3 elements so an element from each of the sets sums to 0 if and only if they're indexed by the same number. Then we have the same bound on M as in this theorem. And this is a generalization because if we take x to be a, y to be a, and z to be minus 2a, then if we have an AP-free set, then we obtain 3 sets that have this property. And Kleinberg proved that the bounds that you get here is for F. So the bound in the multicolored sum-free problem over F2 is sharp by the exponent is sharp by a construction of Fu and Kleinberg. Okay, so the proof of the Capset problem is actually rather short and nice, so I'd like to present an overview of that proof. And it's a very nice algebraic proof. So it uses the polynomial method. So fix p, and fix a prime p, and then we look at polynomials. So let's let m and d be the set of monomials of degree at most d in m variables, so total degree at most d, such that its degree is less than p in each. Now, the point of it being less than p in each is because in terms of functions, you don't gain any more functions by having a higher degree in fp. So now let's fix a polynomial q of degree d. So this is kind of this lemma. So what I'm presenting on this slide basically appears in the Croot-Lev-Pach paper, although it's formulated a bit differently for p equals 2, and then it was extended by Ellenberg and Gijswijt in their proof. So fix a polynomial q of degree d, and then we define this matrix mq. So its rows and columns are indexed by fp to the n, and it has entries p. Basically, the entry x corresponding to the vector x and the vector y is p x plus y.
Q is P?
Sorry, yes, q is p. Sorry. So then the key lemma that kind of makes all this possible is that the rank of this matrix, MQ, is at most 2 times mn d over 2. Now, why is this the key? Why do I say it's the key lemma? So it's not difficult to show that the rank is at most mn d, but mn d half is in general much smaller than mn d. So kind of to illustrate this, if n is large compared to d, then kind of the distribution of the degrees of monomials in n variables is kind of a very concentrated distribution. And so if we take d to be about 2/3, which is what we're later going to do, and d half to be about 1/3, then this is kind of a huge decrease. And how do we prove this lemma? So we write q x plus y. So this is the sum of many monomials of degree at most d. So each such monomials, it's either the x term or the y term has degree at most d half. So this isn't a unique decomposition, but one way to do it is to collect all the terms where the x monomial has degree at most d half. And then in the remainder terms, the y monomial must have degree at most d half. And so we can write the sum in this way. And now this is actually now for this matrix, this is in fact a decomposition of this matrix into 2 mn d half matrices of rank 1. Right? This, when it's indexed by x and y, this is a matrix of rank 1. Are there any questions about this or anything so far? Okay. So So now, how do we use this? So I'll present the proof for the multicolored sum-free problem. So take x, y, and z as in the problem. So again, what that means is xi plus yi plus zi equals 0, but any other triple sums to non-zero. And then the claim is that we have the bound on M of, so for any t, basically we have this bound of at most 2 times the monomials up to degree t, plus this is the monomials with degree above 2t plus 1. And how do we prove this? So we can take a polynomial q of degree at most, so let's assume 2t is large enough. So if we take a polynomial q that has degree at most 2t plus 1 and vanishes on the complement of z and is non-zero on this many points of z. Why is that? So the complement has p to the n minus m points. So this is the dimension of the vector space of all such polynomials is mn 2t plus 1. The complement of z has p to the n minus m points, and you can show that this can be done. So the dimension of the space of polynomials that vanish on the complement of z is mn 2t plus 1 minus p to the n minus m, and then one can show that then there exists a polynomial whose support has at least the dimension of has at least size of the dimension of that space. And then, so we have this matrix Q with the sums, and let's look at the submatrix indexed by x cross y. So so we kind of have a bijection between x and y. So if we're off the diagonal, then that means that we have xi and yj for I and j not equal. And then we know that we're not in z. So then this mq off the diagonal must be 0. If we take a diagonal element, then we basically obtain the polynomial at z corresponding to that at zi. So what this means is that we know that we have this number of non-zero elements in the diagonal, so the rank of this matrix MQ is at least this number. On the other hand, we saw previously that its rank is at most 2 MNT. And so this gives us the inequality, mn 2t plus 1 minus this number is at most this. And if we rearrange it, we obtain the inequality given here. And then if we choose t to be roughly 1/3 times, so p minus 1 times n is the total possible max degree. So if we choose it to be about 1/3, then this p to the n minus mn 2t plus 1 is kind of the monomials here, which is basically the same as the monomials here, and we obtain the bound 3 times mn p minus 1 times n over 3. And then if you just care about sum bound, you can use Bernstein's inequality. If you want the exact number, and which they do, you use Kramer's theorem to show that that gives an exponential decrease in the upper bound. Are there any questions about this?
Got the bound.
Yeah, so these monomials, their degree at most p minus 1 in each variable. So it's basically x1 to the I1, x2 to the I2, xn to the In. And each of these goes from 0 to p minus 1. So what's the distribution of their sums? It's basically a number from 0 to p minus 1 times n. And if we take t to be p minus 1 times n over 3, I'll leave off the integer part, then here we have 2 times mnt, and this p to the n minus mn 2t plus 1 will be the same. So then this gives 3 times mn p minus 1 times n over 3. So another way to think of this is we have p to the n total monomials. If we take a random one, then we basically have n random variables that are each 0 to p minus 1. What's the probability that they sum to at most p minus 1 times n over 3? Their expectation is p minus 1 times n over 2. And so we get an exponential decrease. And we can calculate the exact exponent using Cramer's theorem. OK. So now let me move on to the arithmetic removal lemma. So again, if we have fp to the n, we'll say 3 elements form a triangle if they sum to 0. And Green proved an arithmetic triangle removal lemma, which says, so it's basically the arithmetic analog of the triangle removal lemma. So for any positive epsilon and a prime p, there exists a delta greater than 0, such that if we have 3 sets that have a small number of triangles, so here the total possible number of triangles would be fp to the n, because x and y you can choose anything, and then z, the choice of z is fixed. And so if we have a small number of triangles compared to how many we can have total, then we can delete a small number of elements and remove all triangles. And Green, the proof that Green gave works for general finite abelian groups. So he develops a Fourier analytic arithmetic regularity lemma and uses that. So later, Kral, Serra, and Vena gave a proof which holds for general groups, which basically uses the triangle removal lemma for graphs. So I believe I can briefly sketch the proof. So we take 3 sets of, so suppose we have these sets x, y, and z. We take 3 sets of vertices, each corresponding to the points in fp to the n. So now if we have a point in each of them, we connect u and v if their difference is in x. We connect v and w if their difference is in y. And we connect w and u if their difference is in z. Now, if we have a triangle, so I'm presenting it for abelian groups, but this works for general groups. So if we have a triangle, then that corresponds to exactly big N triangles in the graph, where big N is the size of fp to the n. And vice versa, if we have a triangle in the graph, then that must come from a triple x plus y plus z. And so since we had delta n squared triples, we have at most delta n cubed triangles, which means that we can remove epsilon n squared edges to get rid of all triangles. And now, if we have a point in x, we remove it if at least, so it has n edges corresponding to it, and we remove it if at least a third of the edges corresponding to it are removed. And so then any triangle x plus y plus z, at least one of the 3, it corresponds to n triangles here, and at least one of the 3 points must have been removed. One of the 3 edges must have been removed n over 3 times. Now, so the removal lemma has implications to property testing, or it's very closely related to property testing. So this was initiated by Rubenfeld and Sudan, and subsequently by Goldreich, Goldwasser, and Rahn for combinatorial objects. So the general idea is we look at functions f from some domain to some range R. And we have a property of these functions, so which is basically a subset of these functions. And now we say that a function f is epsilon far from satisfying this property if there's no other function f prime that can be obtained from f by changing the value on at most an epsilon fraction of the points. And a typical property testing problem is to quickly decide whether a function satisfies this property or is epsilon far from satisfying this property with good probability. So if it's kind of between the two, then the algorithm wouldn't be very good. But if it's either satisfies it or is far from it, then the algorithm works with a very good probability. And we think of D as being a huge set, and we make queries for certain elements of D. What is the value of f of D? And we want to determine, again, if we have a function that we know either satisfies it or is epsilon far from satisfying it, we want to determine whether the function is in P with only using a small number of random queries. So, for example, we can look at a triangle-free. So D is a domain.
D is a domain and P is
a property.
property of functions. Okay.
Yeah.
Right.
So, for example, let's say the domain is kind of 3 disjoint copies of fp to the n, or in other words, we have a triple of functions f1, f2, f3, which we can think of as the characteristic functions of sets, and the property is this triangle free. So if x plus y plus z, we cannot have each of these be equal to 1. Now, using the arithmetic removal lemma, we know that if a function is epsilon far from being triangle free, then we in fact have a large density of triangles. So if we start querying random points, random x, y, and then if they're both 1 according to the function x plus y, then based on how the delta from the lemma, we can say that if we have a certain number of queries, then with high probability, if it has a triangle, we will see it. And the point is that because the bound on the density depends on epsilon, but it does not depend on n, here we only need the number of queries we need depends only on epsilon and not on n. So if we have a good bound for the removal lemma, then that implies a good upper bound for the removal lemma, then that implies a good bound on the number of queries in terms of we need in terms of epsilon. So one question is, can we test it with a polynomial in 1 over epsilon queries? So I promised to talk about the bounds, so I'll talk about the bounds of the removal lemma. So let t be this tower function. So that means we take t1 to be 2, and tn, so tn is a tower of 2's of height n. So basically tn plus 1 is always 2 to the tn. And this function grows enormously. So even if we just take t5, then we have a tower of 2's of height 5. So that's already 2 to the 65,000, which is, I think, way more than the number of atoms in the universe. Now, Green's proof of his removal lemma gives a bound. So it gives an upper bound on 1 over delta, which is tower in a polynomial of 1 over epsilon. So this is obviously very huge, which means that delta is actually very, very small. So you would need to take a very, very large n in order to actually see the implications. And so we have a similar kind of bound for the graph theoretic triangle removal lemma, which means that the Kral, Serre, and Vena proof gives the same kind of bound. Now, Jacob Fox improved the bounds in the graph triangle removal lemma. Instead of t of a polynomial in 1 over epsilon, we have t of log 1 over epsilon. So that's, in some sense, a huge improvement. Of course, it's still enormous. And so using Kral, Serre, and Vena's proof, we have the same kind of bound for the arithmetic triangle removal lemma. Now, Hatami, Sachdeva, and Tulsiani gave a kind of Fourier analytic proof, so it doesn't go through graphs for f2 to the n, but that gives a similar kind of bound with this tower of log 1 over epsilon. Now, if in the case of f2 to the n, Bhattacharya and Xi gave a lower bound of approximately 1 over epsilon to the 4.847. And Fu and Kleinberg gave a lower bound 1 over epsilon to the 13.239. This is an explicit number minus little o1. And but until recently, nothing better was known, even for the specific case of fp to the n. So using the Ellenberg-Gijswijt results, with my advisor, we can prove a polynomial bound on this for Green's triangle removal lemma if we fix p. So for p equals 2, we get a number C2 1 plus 1 over 5/3 minus log 2, 3. And this is the same number that I had on the previous page.
So this is nothing bound.
Yeah. Yes. Well, so the way this is an upper bound on 1 over delta. So it's a lower bound on delta. And theirs was a lower, it was basically a construction, which gives, yeah. This is opposite. So this is a general, so this improves this result. And in general for P, we get an explicit bound. And so through personal communication with Kleinberg-Speyer and Selwyn, they're apparently currently writing up a proof that shows that this is tight for general P. Okay, so how does this proof go? So first, we assume that we have these 3 sets x, y, and z that are disjoint, and we again denote n as the size of f2 to the n, and each element is in exactly the same number of triangles, so some delta n. And then we want to show that, in fact, x, y, and z must be small. So let's take a random subspace of dimension log 1 over 5 delta. So basically, the size of this subspace will be approximately 1 over 5 delta. And then take the intersection of each of these sets with this subspace. And now we call the triangle good. I'm sorry, that should be x prime, y prime, z prime. If it is the unique triangle once we intersect with this subspace for each of these 3 points. And now we further, so we define x tilde, y tilde, z tilde as subsets of x prime, y prime, z prime, the set of points that are in good triangles. And so for an explicit C, something like 1 over 100 or 1 over 1,000, we show that the expectation of the size of x prime is at least a constant times the expectation of the size of, so the expectation of the size of x tilde is at least constant times the expectation of the size of x prime. And further, it's not difficult to show that the expected density of x prime is up to small errors about the same as the density of x. So how do we show this? So we want to show this claim. So first, I want to argue that if we have a triangle x1, y1, z1, and we know that that is contained in W, then we have a good probability that it's a probability 3/5 that it is good. So it's the only one that each of them is contained in. So let's look at x1. So x1 is in T triangles. And because I said that x, y, and z are disjoint, these T triangles correspond to T different two-dimensional subspaces. I'm sorry, I forgot to mention that I'm going to concentrate on the F2 case, which is slightly simpler than the general FP case. So the probability that one of the other ones, conditioned on this being in the subset, is approximately 2 to the d minus n. There are some lower order terms in the fraction here. And now we have, so we know that this one is in our subset. We want to say that none of these are in the subset. So the probability of that, so we have t minus 1 of them, and each of them it's approximately 2 to the d minus n. So using a union bound, we have approximately delta times 2 to the n times 2 to the d minus n. And since 2 to the d is roughly 1 over 5 delta, this gives us an upper bound of 1/5. Okay, so what we have here is that if we have a triangle contained in x prime, y prime, z prime, then with probability 3/5, it's good. So now, if we just have that x1 is in this x prime, what's the probability that it is good? So we have, again, it's contained in t possible triangles. For each of these, there's approximately, again, 2 to the d minus n probability that it's contained in our subset. And if it is contained, then with probability 3/5, it's good. And now these t events here are disjoint because each of those events is basically saying this one triangle is good, this one triangle is contained in the subset, and none of the others are. So these t events are disjoint, so we can get a lower bound by t times this number. And again, this gives an explicit constant c tilde. So where these c's come in is the fact that 2 to the d is not exactly 1 over 5 delta, it's in a range, and similar, it comes in from smaller order terms, but it's an explicit constant. Okay, so we saw that this expectation is at least a constant times the expectation of x prime, whose density and expectation is at least the density of x. So that means that we can take a subspace of dimension d where the set of points in x that are in good triangles is at least a constant times, so the density of points in good triangles is at least a constant times the density of points in x. Now, if we only take the good triangles, then this is actually a sort of multicolored sum-free set. So the union of these forms, so kind of if the three sets are indexed by which triangle they're in, that gives exactly a case of this multicolored sum-free sets. So that means that we have a bound on the size of x tilde of size 1 minus c2 times d by the argument of Ellenberg and Gijswijt. And then if we divide by 2 to the d, then we have that this x tilde has density at most 2 to the minus c2 times d plus a lower order term, which is basically delta. So 2 to the d was basically 1 over delta. So this is basically delta to some exponent plus an error term. And here by little o1, I mean that as delta goes to 0, this error term goes to 0. And so this implies the same bound for x up to a constant factor. Now, so here we said this is if each of the elements is in the same number of triangles. So this same proof goes through if they're in roughly the same number of triangles. So at least delta 1 and at most delta 2. And we get an upper bound delta 2 to this exponent times their ratio. And here, this delta 2 and delta 1 are not going to be a constant factor apart. They're going to be a log delta factor apart. Are there any questions about this? And now for the proof, we show the following claim. So suppose we take epsilon n disjoint triangles, then if we take kind of the union of the x i's for x, y i's for y, z i's for z, then just among those sets, we must have at least delta n squared triangles. So why does this prove the theorem? Basically, the number of disjoint triangles we can take in a triple x, y, z estimates the number of points we need to remove by a factor of 3. So in one direction, if we have these disjoint triangles, we must remove 1 from each of them. On the other hand, if we just start greedily removing triangles, and so then we get a set of disjoint triangles, and if we greedily remove each edge in the triangles, then if we can't get any more, if we can't extend the set of disjoint triangles, then if we remove the edges in all of them, then what remains is triangle free. So we just need to show this claim. So now we want to kind of equalize the degrees. So first, if we have a point whose degree is too high, then we delete it. So if at some point we have density delta prime, if we have a point, so on average, since we have epsilon n points, we would have delta prime over epsilon degree. So if it's higher by a square log factor, then we delete it, and then we update delta prime. And we keep doing this. And because of this log squared factor, we can show that we delete at most a fraction of the points. So as basically due to the sum of an infinite series, because of this square here, ends up being finite. And so when this process ends, so we've gotten rid of the points of high degree, and we've kept at least a constant fraction of the epsilon n points. So then after that, we delete points with degree less than delta prime over 6 epsilon. And since we have at most epsilon n points in each set originally, we end up deleting at most delta prime over 2 fraction of the triangles. So we keep at least a delta prime over 2 fraction of the triangles, which implies that since we have an upper bound on the degree of any point, we have at least epsilon over polylog 1 over delta points remaining. So now we can apply the previous lemma with delta 2 and delta 1. And we get, so I've moved the polylog to the right side here, but we basically get this to the power of c times their ratio. So this gives some log factors, which I've moved here, and then it gives that epsilon is at most this delta prime over epsilon times to the c2 times some polylog terms. And then if you rearrange this, this gives epsilon is at most, so this gives that epsilon to the 1 plus c2 is at most delta times polylog delta. Delta prime, which is at most delta, and then we can reverse this to obtain the polynomial bound on delta in terms of epsilon. Are there any questions? Okay, so there are still many further questions in this area, so I'll just list a few. So we generalized the Capset problem by saying that 3 points form a 3-term arithmetic progression, but you could also generalize it to P. So for F3, this was equivalent to saying that there's no affine line contained in our set. So an open question is, if we have a subset in Fp to the n, where P is bigger than 3, how large a set can we have that contains no affine lines? Can you get an exponentially better bound, or is it P to the n divided by just sub-exponential? Another question is, can any of these techniques help with Roth's theorem? And another open question is, can any of these techniques help with the graph-theoretic triangle removal lemma? So for the graph-theoretic triangle removal lemma, there's no polynomial lower bound by a constructive Behrend, but still the lower bound is roughly 1 over epsilon to the log 1 over epsilon, and the upper bound is this tower, but due to Fox's proof. So there's a huge gap there. And Thank you for your attention.
Any questions?
I have a question about your question 2. So because of the lower bound, you cannot hope to have such a big improvement for Ross theorem, right? So there in fp to the n, you get an improvement which is polynomial in the size of fp
Yeah,
to
you
the
do
n.
not have a polynomial, but
So it doesn't mean, naively maybe it means that those techniques cannot help, but that's not the case.
well, I mean, yeah, maybe the answer to this question is just a simple no, but it might be worth looking at. So.
Can you say a few words about the Kleinberg construction and the construction that means that this is tied in? Can you see that construction somehow?
Right. So this proof, I mean, for F2, this proof basically shows n choose n over 3 times a constant, and their construction, I think, is n choose n over 3 times e to the minus, I'll just write c root n. And they basically take x as a subset of the sets of size n over 3. Actually, this is probably too low for anyone to see. So basically, okay, so they take x as a subset of n over n over 3. Y also, so weight, so these are coordinates of weight n over 3, and z to the coordinates with weight n over n divided by 2n over 3. And now this doesn't work because, well, clearly it doesn't work. But then, well, I don't want to go into this proof, but they kind of take random subsets a certain, I'll just say they take random subsets a certain way to kind of weed out the, they basically construct a lower bound for the multicolored sum free problem, and they kind of weed out bad sets in a way such that what they're left with is a good case of the multicolored sum free problem, and they can show that with that in expectation they keep enough of these points. I don't know more of this proof off the top of my head, but.
Any further questions? Let's hear that. Okay.